All right. Thanks, Professor Rottengruber, for the nice introduction, and welcome to our talk. Our talk is about the requirement definition for vibrating components, so what you put into a component specification sheet with using transfer path analysis and especially blocked forces, which we've already heard about today, and a method called solution spaces, which I think is interesting enough to present here. So, we want to define a requirement on the vibrating active components coming from a overall system target. And you know, that's easy to define. This picture kind of defines it for me. I've got 2 daughters in about that age, and when we are in the vehicle, we want it to be our kind of safe space and want to have a safe ride, such that the kids can sleep and maybe I can have a good talk to their mother. And there's many potential intruders to this quietness and comfort that we want to achieve in a car. And it's too much to list all of them here, but this is all components that we deal with at Vibes, also in terms of blocked forces. We've heard about this today. We're also working on road noise, steering gears, ear motors, e-compressors, water and air pumps. And as you all know, at the beginning of a vehicle engineering project, you need to define component NVH targets, and you just don't know yet what the vehicle is going to be like. And to make matters worse, you have structural dynamics and physics, and we know that the vibration levels and the force levels that you could measure on a test bench or in a vehicle, they will all be very different, because the structural dynamic quantities are a property of the coupled system. It's a highly coupled system, so your test bench assembly is going to have very different resonances than your vehicle, and you are faced with this challenge on how to define meaningful component targets for the structure-borne sound path. All right, so that brings me to the question how we came into this. Our customers asked us this question a lot, if we could help them there. And to explain this, I have to give you some background on blocked forces and what we do at Vibes, and then I hope it becomes clear to you why we think that there is an emerging trend in how to come up with component NVH targets. So I'll first show you a big picture of what we do at Vibes. We've already heard about substructuring and blocked forces, and this is exactly the reason that Vibes was founded. So we've been a series of, I would say, 15 years of PhD research and a lot of master theses, especially under Professor Rixen, who is formerly at the TU Delft and now at the TU Munich. And Vibes, founding Vibes is really the effort of maybe some PhD students trying to heal their collective trauma from the research phase that they had in MATLAB and all the experimental things that can go wrong. And we're trying to make software to make this accessible to industry, because it's actually quite nice to be able to, like Lego blocks, assemble your structures and choose the easiest and most accurate approach for each of your substructure in the transfer path that you have. So either an experimental model, a simulation model, sometimes for rubber bushings, just analytical models, and then simulate the transfer path of the whole assembly. And then the last thing you need, if you want to know what the sound in the driver's compartment is going to be, is some way of describing the source activity, so some kind of forces. And we've already heard today that blocked forces are, in principle, a good way to do this. So I'm just showing it here in a high-over picture. You have in blue a source component, could be one of the components that I've shown before. There is some internal forces acting there, exciting this component in operation. They are hard to simulate, hard to measure. And it's exciting the receiver, shown in gray, which could be the car, and creates some sound pressure and vibration signal at the driver's ear, seat rail, whatever. And the blocked forces are, in theory, the forces that you would get when you would measure the reaction forces against an infinitely stiff test bench, right? I mean, making an infinitely stiff test bench is infinitely hard, so we've already heard that there's different methods to determine these blocked forces in practice. And this is this whole family of component-based TPA methods, which are basically just answering the question, how do I really determine these forces in practice? But the cool thing about the blocked forces are that if you work out the equations, there's a nice analogy with active noise cancellation, how you can derive this without many formulas, but you can also read the paper. But it turns out you can use these blocked forces, which are an independent quantity of this source component, right? It does not depend on the dynamics of any receiver. It's the forces against a theoretically rigid interface. And if you have these, and you have the transfer path of the coupled system, the full vehicle, then you can make physically correct predictions for the sound that the drivers hear without any crazy assumptions other than linearity of your system. And that the internal force excitation is the same on the test bench as in the car. But that's typically a given. So you see, blocked forces are independent from the testing environment. It can be used as a simulation input, but I hope you see that the approach or the question we got from customers is, hey, can we not also use this for defining good and more meaningful targets for our noise components in the component specification sheets? And here I just have a small example that I like to use in seminars that we give about the method and how to apply it in practice. That's basically a small e-motor that you see. On the top left picture, it is mounted on a receiver structure of 2 plates with rubber bushings. And here in the bottom picture, it's attached to a different receiver, which is again these 2 plates, but just with very thin and stiff rubber bushings in the middle. So the receiver has very different structural dynamics. And we determine with the in situ method the blocked forces in these 2 different receiver conditions. And also with a classical TPA approach, we determine the interface forces. And if you do that for this e-motor, you see that on the left, these blocked forces are very similar in both designs. They're not perfectly the same. It's an experimental model. And we can talk a lot about how to model the interface with how many degrees of freedom. That's actually very important. But we're not going to go into that. But the important thing is, you see on the right, the interface forces, and that's what I mentioned, right? So if you measure interface forces, the real physical forces that act between the 2 structures, they are always a property of the coupled system. So on whatever test bench you put your component with different structural dynamics, you will measure different interface forces and different vibration levels in general, unless you have some assumptions which are valid about high decoupling and soft rubber mounts or so. So that in principle makes these blocked forces an interesting quantity to derive component NVH targets. So the example we gave Mr. Xu, who's going to explain you more on how to find a structured way to determine these component targets. And we started with a simple example here of a damper. We've worked a lot on damper rumbling noise in a project with customers. And that's one example with an easy interface description, because the main contributors, you can see on the right a partial contribution plot, is actually the top connection point in the Z direction. It's basically pushing into the body and is transferring this rumbling noise. So the task here, just as an example, would be to derive a component target for this damper that you can give to your supplier based on the vehicle target, which I've shown at the beginning, the comfort in the driver's cabin. And Mr. Xu is going to explain you a bit more on how to do that in a structured manner with solution spaces.
Yep. Thank you, Mr. Häußler. Hello, everyone. Before we could define targets or compute, or in other words, compute requirements for this damper, we start to develop our method with a simple mass spring system, which only has 3 degrees of freedoms, but still can represent the general vibration propagation problem from the unknown vibration source, U1, over interface U2 to the receiver, U3. So to keep it simple, At first, we ignore damping and assume that the transfer function and the block force are both real scalar. And for this example, there's only one degree of freedom at the interface. So we define the system level requirements as the sound pressure, P3, which is computed as the transfer function multiplied by the block force, to be smaller than our target value, P tilde. Based on this equation, the upper limit value of the block force can be computed simply as P tilde divided by the transfer function. And due to the positive and negative sign, there's also a lower limit value, which is the negative counterpart of this upper limit value. So it means that in order to make sure our noise level is smaller than a limit value, the block force must stay in a value range bounded by this upper and lower limit. Compared to this simple example, practical applications are more complex in two ways. First, the damping would make the FRFs and the block forces complex numbers. Second, the interface usually have multiple DOFs. So in the following, we try to develop our method further to first to address the issue of complex numbers, then the issue of multiple interface DOFs, and in the end, these two issues combined. So when the transfer functions and the block forces are both complex, they can be represented with their real and imaginary part. Finally, we can compute these component level requirements through analytical derivation. And it's given by this equation. It can be interpreted as a circle on the complex plane when the real and imaginary part of the block force are plotted against each other. So we concluded that a circular area is suitable to describe the admissible area of a complex block force on the complex plane for a certain frequency. So after solving this first issue of complex numbers, we move on to take a look at the issue of multiple interface DOFs. Again, we take this mass spring system as example, but this time we treat U1 and U2 both as the interface. So it means that U2 and U1 both contribute to the noise at the receiver. And to keep it simple, at first we ignore damping. So both the transfer function and the block force are real scalars. Again, the sound pressure at the receiver can be computed as transfer function Y31, Y32 multiplied by the block force F1 and F2. Through analytical derivation, we can compute the component level requirements as this equation. This can be interpreted as two boundary lines when F1 and F2 are plotted against each other. So this is the upper boundary, this is the lower boundary. It means that in order to make sure the sound pressure at the receiver is lower than the limit value, the combination of F1 and F2 must stay in this area bounded by these two boundary lines. But this complete admissible area is not ideal to be used as requirements directly, because for applications with more interface DOFs, the shape of this admissible area for the block forces will be very complex due to the interdependency of block forces. As a result, it will be very difficult or even infeasible to compute or formulate the form of this admissible area either through analytical derivation or a numerical method. So we propose to take just the subset of the complete admissible area. For example, here we can define a box-shaped solution space. Based on this solution space, we can identify the admissible value range for F1 and F2 individually. As a result, we can formulate the requirements as individual admissible value range for F1 and F2, bounded by their lower and upper limit value. This is what we called the solution space method. So I will introduce this method shortly. Actually, the solution space method is a family of different methods. They all based on modeling between design variables and quantity of interest. In our case, the design variables are the block forces. The quantity of interest is the sound pressure. Based on this modeling, the solution space method explores the design space using random sampling. As can be seen here, good designs are marked in green. And the core idea of the solution space is to just define a subset of the complete admissible area. And based on this subset, individual admissible value range is identified for each quantity. The requirements is formulated with these value ranges. Since the solution space formulates the requirements as a value range, it provides robustness and freedom for the component designer in contrast to numerical optimization, which in principle only provide one single optimal value. Also, by doing so, the requirements on different quantities are decoupled automatically. Through this decoupling, the interdependency between different quantities are broken, and therefore the formulation of requirements is largely simplified. Since there are only good designs in the subset, so the component requirements defined in this way is very well in line with the system level requirements. As long as this component level requirements is fulfilled, the system level requirement is in principle guaranteed to be fulfilled. So with this solution space method, we can finally compute the requirements for the most general cases where there are multiple interface stops and the transfer function and block forces are both complex numbers. So again, this sound pressure is computed as transfer function multiplied by the block forces. Here we have 4 design variables, which are the real and imaginary part of F1 and F2. Therefore, we cannot compute the requirements analytically through analytical derivation anymore. Instead, the solution space method provides a powerful numerical tool for computing the requirements. As we know from the previous research, the circular area can very well describe the admissible area for the complex block force. So here, again, with the solution space method, we compute the circles for both forces through numerical sampling. So to summarize, we notice that as the complexity of the design increases with increasing number of interface stops and with damping taken into consideration, the analytical derivation is no longer enough, and the solution space method provides a very powerful numerical tool. So in the end, we implement this method onto the damper problem. For demonstration purpose, we have created such a user interface in MATLAB. In the first step, we define the system level requirement as such that the aviated sound pressure level must be smaller than a certain limit value or frequency. Correspondingly, the unweighted sound pressure level has a limiting curve, which is marked in blue, which is a decreasing curve over frequency. Then we can compute the circles for each frequency based on this equation. So the complex block forces are sampled. For each sample design, we compute the sound pressure based on measured FRF of a real vehicle. In the end, all the circles are summarized and visualized by connecting them over frequency. So in the end, this is the computed requirements for the damper. So through this process, we can compute the requirements for the damper based on the system level requirements. So it's kind of a process of target cascading. With these requirements, we can select good products. For example, here we have taken 2 products as an example. The block force of the first damper is larger than requirements, especially in the lower frequency range. And the block force of the second product is smaller than the computed requirements. It means that with the second damper, the sound pressure level of the vehicle is smaller than the limit value. And with the first damper, it would be too loud. To validate our method, we have inserted these 2 products into the vehicle virtually. It means that we compute the sound pressure level for both products by computing the transfer function, by multiplying the transfer function with the block forces of both products respectively. As can be seen here, with the bad damper, the noise is higher than the desired level, especially in the lower frequency range. But with the good damper, the requirements are very well fulfilled, almost in the whole frequency range. Okay, to summarize, the block force is a property of the vibration source and is independent of dynamics of the transfer path, which makes it an ideal quantity to characterize the excitation of the vibration source with the transfer path analysis. And the solution space method offers a powerful numerical tool to compute requirements on the vibration source. So if we combine them together, we can compute the requirements on component or specifically on vibration source in a quantitative manner. And although we only show the example with 2 interface stops, it's actually also valid for for applications with more interface stops. And it can be also used to compute requirements on other vibration sources. In the next step, we will try to examine our methods on more applications and also try to compute requirements on other quantities. Next to block force, the following quantities are on our candidate list. For example, the free velocity, equivalent power, interface force, interface velocity, and interface power. One drawback of the block forces is that if application has many interface stops, it would be difficult to compute requirements on each block force. So in this case, it might be more convenient to compute requirements on power, which is summed up over our degree of freedoms. So we have tried to apply the solution space method to compute the requirements on the equivalent power. In the end, the requirement is formulated as an upper limit curve, here shown in the 1/3 octave band. Unfortunately, due to time reason, I cannot go into details. But if you are interested in our research, please feel free to contact us or hire me, because I'm looking for a job. Thank you.